First off, there were 3 incorrect solutions on the quiz. Please, if you think you have an answer correct and you're surprised, send me email. I give extra credit when someone points out an incorrect answer. And I know it seems amazing and remarkable, but yes, professors get things wrong too, especially when they rush out a quiz like I did on Tuesday night because I was trying to have it ready for lab the next day. And that happens. So at any rate, question 2, the answer to the binomial was wrong until about 10:40 today. The answer was 35, not 8. And then on 4 and 5, it said to give me the numerator and denominator vectors when you were dividing 2 binomials. And the question explicitly said, do not perform cancellation. But of course, my answer performed cancellation. So that was also, my answer was incorrect. So Canvas does not have an automatic regrade feature, which I find to be amazing since all you should have to do is regrade the quiz. So I will be manually regrading the quizzes this afternoon. So many of you will be seeing your scores go up by some amount. If you did the quiz right before class, you probably won't because by then the answer was corrected. And the reason I had you do that quiz is because what I'm discovering is many of you are diving into the lab without understanding how to do it. Okay, so if you don't know how to compute a factorial, if you don't know how to compute a binomial coefficient, if you don't know how to compute an expected value, then you won't be able to write the code. Okay, but what I'm seeing is students come to my office, they're trying to write the code and they don't understand what the problem is. So the point with the quiz, and I may be doing this in the future too, is to try to get you to be able to work it through on paper. I can't emphasize strongly enough how working through some concrete examples on paper will give you an idea of how to tackle the lab. So I'm just trying to find different ways to force you to work it out on paper before you write code. Okay, so that was the point of this quiz. And there are 3 things I do want to point out today. 2 of them with the lab and 1 kind of a tip. So we'll start with the lab. So the first thing is a reminder. Even after you do cancellation, you probably won't be able to multiply the numerator and the denominator together. So if even after cancellation, you may have terms that look like this. Okay, if you have terms that look like this and you try to multiply out the numerator and the denominator, it's still not going to work. You're going to get overflow, infinity divided by infinity. So what you're going to have to do is kind of stepwise division, such as 80 divided by 100 times 79 divided by 99 times 78 divided by 98. But it's a little easier than that, it turns out. So the easier way for this lab is, we'll just give you 2 vectors, 1, 2, 3, 4, 5, 6, 7, 8, and a second one. And these vectors are much smaller than what you'll normally have. So let's say this is the numerator and this is the denominator. And we'll have, say, 3, well, it doesn't matter what your value for 1 is. So we'll have, say, 3, 1, 5, 2, 3, 6. So the way you want to perform your multiplication is you want to step through both arrays at the same time. And I suggest that when you do your multiply and divide functions, you always keep the 2 vectors the same size. This is a case where it's a small program. Keeping the 2 vectors the same size isn't going to affect either the running time or the storage very much. So it just Makes it easier if you keep the two vectors always the same size. So what I would do is simply roll through the two vectors. So in this case, it would be basically for I equal 2 to 8. And again, I'm using pseudocode. But basically, what you do is you figure out whether the numerator or denominator is greater. So basically, if the numerator is greater than denominator, then and that's just for that term. So basically, if numerator I is greater than denominator I, then multiply the product by terms, or multiply product by I How many times would I multiply the product by I? If the numerator of I is greater than the denominator of I, how many times should I multiply the product by I? So it's going to be by the numerator of I minus the denominator, because there are three, in this case with 2, there are 3 2's and 1 2 in the denominator, so the cancellation means there's only 2 numerator terms. That's how you do cancellation. You simply subtract one from the other. And then else, I'll let you figure out the else part, but the else part is that the denominator is greater than the numerator, so perhaps you should divide the product by that number of i's. So I'll let you figure out the rest, but what you're doing is you're simply, sometimes you're multiplying, sometimes you're dividing, but by doing that, you're keeping the product from ever getting to be either too big or too small. Okay, so that's hint number 1. 2 is more of a just observation. You don't really have to do it. But in the print function, you have to print out, after canceling terms, you print out some stuff in the numerator and then some stuff in the denominator. Maybe like that. And the issue is when you go through, one way to do this is to go through first the numerator vector, and every time there's more terms in the numerator vector than in the denominator vector, you print out the numerator. And then you make a second pass after you're done printing all the product terms. So once you're done printing all the product terms, then you make a second pass through to collect all the quotient terms, which is a natural way to do it. But you could also make one pass through if you used O-string streams. So if you used an O-string stream, you could have 2 string streams, one for the product, or I'll call the other one for the quotient. And so you could simultaneously be creating the strings for the product, which is on top. This would be the product. And this would be the quotient. And then you'd only have to make one pass rather than 2 passes. Not saying you have to do it this way, but to this point in the course, we've always pretty much just used I-string streams to break things apart. And I just wanted to point out, you could actually use O-string streams in this case because you can actually build up the quotient part of the string as you are building the product string, but you can't print it yet. You have to defer the printing of the quotient string until you have completed building the product string. But with an O-string stream, you can defer that printing of the quotient by building it up in an O-string stream and then printing it out when you're finished. So that's a nice use of an old string. The third thing is a definite tip with pointers that is very important. So I looked at some of the Lab 5 code, and one of the things I was often seeing is stuff that looks something like this. Bitmap star BM equals new bitmap. Okay, and then immediately BM equals M copy. This is really bad code. Really bad, okay? The reason is you have a big old memory leak when you do this. Every time you call, what happens, this statement creates a new bitmap, which can be a pretty significant object, consuming a lot of storage. And you now point to that. So that's one. Now, in step 2, you create a copy. And you make BM point to the copy, which means you lose the pointer to this object right here. And it becomes what we call a memory leak, because you never reclaim its memory. And if you end up calling this function a million times, you're going to run yourself out of memory, because you never reclaim this object. So this is a really bad habit to get into. Okay? Now, you might say, well, what if I tried to delete it? Well, why even bother creating it? You never used it. Okay, I know a lot of you think, oh, I have to initialize BM. No, you don't. You're initializing BM in step 2. The only reason you initialize something is because you have to use it before you assign another value to it. In this case, you don't use BM before you assign another value to it. Okay, so step 1, where you do the initialization, not only does it create a memory leak because you lose the object, but you never even use the object, so you waste time as well. So this is an example of wasting both time and memory. And in big, long-running programs, this will bite you. Okay? You will run out of memory. And eventually your program will terminate with a memory error. So you absolutely have to get out of this habit. Do not do this. Okay? I'm going to put a big X through it. That is very bad habit to be in. And if I see that on an exam, I guarantee you I'm going to be deducting at least 2 points for doing that. If it's not necessary, and it's not necessary here because you never use that matrix. So what you wanted was just a declaration of BM, and then you set BM to be M copy. Or just say this, BM equals M copy. Okay, that would be fine too. And then you don't even need statement 2. So that's a fine thing to do too. But you really got to get away from you don't want to be assigning matrices or objects to pointer variables that you proceed to never use and also proceed to never deallocate. Okay? Those are memory leaks. When you lose a pointer to an object, the last pointer to an object without deallocating it, that's a memory leak. If you don't remember what a memory leak is, please go back and look at the lectures on pointers, because we talked about memory leaks in that lecture. And memory leaks are very important, okay? Because There are programs that companies put up there that essentially are expected to run indefinitely. And you cannot just be allocating memory and then not reclaiming it. You have to reclaim your memory. So questions about that? Okay. So today, we are going to be finishing up sets and maps, and we're also going to look at some different ways you can access maps. So let's take a look at Dr. Plank's notes. Remember that sets are going to be another way of implementing insert, find, and delete. And sets and maps are useful when we have one of two conditions. One, we have range queries where we need to return a range of values or keys, or two, where we periodically print the elements in sorted order. Not at the end. If we only print the elements in sorted order at the end, there's a more efficient way to do it. But if we periodically print the elements in sorted order, then a set and a map is also a good choice. If we don't have one of these two conditions, typically hash tables are better. Okay? So the API that you're caring about, well, it's probably easier to just look at some examples. So the first thing that Dr. Plank did was to just use a set. If you remember, a set is just an ordered collection of keys without values. And what he's doing here is a very simple sort program. So he's getting lines. He's using the insert function. So instead of using pushback, you use insert. And that inserts the given key into the set. And then just like you did with lists, there are iterators. And you iterate through the collection using begin, end, and plus plus. And you access the elements using star. So it's very much like lists, okay, in terms of the syntax. And just like lists, you tell C++ what type of key it is storing. In this case, it's a set of strings. If you want to use an iterator, just like with lists, you need to tell C++ what kind of collection it is iterating over. So before the iterator, you put a double colon and the type of collection it will be iterating over. So that's pretty simple. And if you were to run this code on some input, then it would print it out in sorted order, because that's what sets do. They keep things in sorted order. So that's a very simple example using insert, one of the three operations we care about. Okay? So what happens if we have duplicate entries? So here we have John Bevy, and again we have John Bevy, and here we have Max inadvertent 3 and Max inadvertent 3. And as you can see, when we print out, what happened? What happened to our duplicate keys? Pardon? There's only one of them. So the other duplicate key went away. So sets cannot store duplicate keys. Nor can maps. So neither sets nor maps can store duplicate keys. But no worries, because C++ has multisets and multimaps that do store duplicate keys and duplicate maps. Now, the mathematicians among you must be shuddering because that is not the definition of a set. But there are times when you do need to store duplicate keys, and so the declaration is simply multiset in that case. And when we do our insert into a multiset, then it does keep all of our duplicate keys. Okay, the second method, very handy. We said we care about insert, find, and delete. And 2 for 3, they're naming the methods exactly after the operations. So here what we're going to do is we're going to get a bunch of names, and then we're going to search to see whether the name, we're going to have a user enter names and see whether they exist. So this could be a phone directory or an internet directory or a class roster where we first enter a bunch of names and then we want to query to see whether certain people are in that collection. Okay, and the basic thing is right here. While we get line from a file, we insert the name into our name set. And here's our declaration. And Dr. Planck, just for grins, instead of getting stuff from CN, was getting it from a file. So the get line was from the file rather than from CN. And then he goes into an infinite loop. I actually would rather you write true rather than 1, but he's old school, he writes 1. But this is really a Boolean conditions, and Boolean conditions evaluate really to true or false. So it really is better to write true here. So you enter a name, you flush, and the reason is sometimes C++ buffers up output, and especially partial lines, and it won't output a line until it receives a new line character. So flush ensures that it gets put out even if the line is just partial, which it is here. There's no new line character yet. Then we try to get a new name, and if it's end of file, that is the user has hit Control D, then getLine will return false and we will exit our program. Otherwise, we do our find. So there's the find, and it returns an iterator. So find returns an iterator. So find returns an iterator that either points to the key or points to the found item, to the found key, or if the key is not found, if the key is not in the collection or in the set, then find returns end. So it returns a pointer. What does end point to? Does anyone remember what end points to? I think I heard it. Sentinel value. End points to the Sentinel value. So just like lists, sets have Sentinel values. So end points to a Sentinel value so end points to a Sentinel value, and find returns in effect a pointer to that Sentinel value if it does not find the key. So if it is equal to names.end, we print out that the key is not in the set. Otherwise, we print that the key is in the set. So that's find. Again, very simple, returning an iterator, always returns an iterator, And you can test it to see whether or not the key is in the set. Okay? And he does not have the third operation, which is for delete, so I will give it to you. Unfortunately, instead of delete, it's called erase. And there are 3 versions of erase. So the first takes an iterator and deletes the item pointed to by the iterator. The second takes a key, very handy, deletes the key if it exists. And the third version of erase erases arrange. So you give it an iterator first and an iterator last, and it deletes all keys in first, last. If you don't know this notation from math, what this notation means is that all keys, including first, what does the right parenthesis mean for my mathematicians in here? Up to, but not including. So the bracket on the left says including first, but the right parenthesis says up to, but not including last. So up to, but not including last. So 3 versions of erase, which is delete. Okay, his notes don't have an example, but those are the 3 versions you should be familiar with. Okay, and sets are nice often for just checking whether someone is in a collection. So I have a problem that you're going to be doing later today where we have voters. And we want voters to only be able to cast 1 ballot. So we're going to use a set to keep track of people who have voted. And that's all we need to keep track of. We don't need to keep track of their ballot or anything. We only need to keep track of whether or not they voted. So a set, in that case, is a good choice. But most of the time, we actually want to store key value pairs. So unlike sets, maps store key value pairs. So also in the problem you'll be working on, we will have candidates, and they will have votes associated with them. So the candidate will be the key, and the number of votes that candidate has received will be the value. So typically we want to store a value with a key. And when we look up a key, what we really are interested in is the value associated with the key. Now, when you declare a map, you declare 2 types. The first type is what? The type of the key. And the second one would be the type of the value. So this is the type of the key. And this is the value type. Everything else looks just like all the rest. So the iterator looks exactly the same. You tell it what type of map it is iterating over. Now, maps, when you insert, so in this case, what we're going to do is we have an example with National Football League players in 2009, and he has a roster that he's inputting, and it includes all the players in the NFL in 2009 whose last name started with A. So first name, last name. And what he wants to do is he wants to count the number of players that have the same first name. So he wants to count the number of players named Alan. He wants to count the number of players named Adams. So there may be duplicates. Okay? So he is storing the last name, and then the int is a count of the number of first names. So the string is the last name, the key is the last name, the value is how many players have that last name. So that's what the int field represents. How many players have that last name? So he's simply reading into first name and last name. Since roster.txt is a file, how is it that he can read from CN? How is he managing that? How does he manage to read from roster.txt using CN?
You redirect it from the command line.
Very good. He's redirecting from the command line. So he's redirecting using the less than sign. Okay, so first thing he does is he checks to see whether the last name is already in the map. And if the last name is not yet in the map because we get the Sentinel value back, we need to create a new entry for that name. And you'll see that now we don't just insert the key, we need to insert both the key and the value. And this is where C++ falls flat on its face. This thing of making a pair is ridiculous. They should just let you have two arguments being the key and the value, but they don't. Java fixed this abomination. But in C++, you have to make a pair. And the way it essentially is defined is that you, in effect, have a class pair where type 1 is the key value, except that, again, they go wrong and they call it first, and type 2 is the value, but they call it second. I mean, if you're trying to come up with a worse interface or API, it would be hard to do so. Okay, this is just true. My research area is graphical user interfaces where you try to make things easy for people to use. This is the opposite. This is being as counterintuitive as possible. Okay, so you just have to remember that first, the field first means the key, and the field second means value. Okay, if I was running an obfuscation contest to see who can write the most confusing design, I would give high marks to this particular individual in this design. Yes?
Can you just do names bracket?
Yes, we'll get to that, okay? So they did do a little bit of a cover for themselves, so we'll get to that. But if you use the insert function, this is how you have to do it, okay? So you have to call a function called makePair and give it the key and the value. Okay, otherwise, this is where you see knit arrow second. So it returns in effect a pointer, and the way you dereference it is with the arrow. The second is the value field, and that is a count. So second, remember, is the number of players with that last name. So if you found the player, they were already in there, so you simply increment the count by 1. Otherwise, you'll notice in makePair, we initialize the last name to have the value 1. Okay? Questions about that? And then at the end, we iterate through, and since the map keeps the items in sorted order, we will find out that everything comes out in sorted order. So when we look at the results, we see that they are in sorted order. And no, this is ABDA, this is ABDU, so they really are not the same last name. Okay, you can see there were a lot of players named Adams. There were 7 players with the last name of Adams. Okay, so that's insert. That showed you both find and insert. And just like sets, maps have 3 erase versions that erase a iterator, erase a key, or erase a range. Okay, we're not going to show you examples of using erase, however. Okay, you could also have done that with a multiset, although it would be a lot more complicated. Okay, so with a multiset, we could store multiple individuals with the same last name. And you can see that here we just are keeping the last name, and we simply insert the last name because we don't care about the first name. We only want to keep a count of the number of last names. So at the end, we might have something like, say, in this last case, it would be Abdallah. Then I believe it would be Abdullah, then Abdullah. And I'm going to skip and pretend there is a bunch of Adams now. So at the end, this is what it would look like. And now you would have to design an algorithm to count the number of last names. Okay, so shouldn't be that difficult. Essentially, what you need to do is you keep track of the current name that you are counting. Okay, and what happens when you move to someone who has a different name? What would you do? Reset the count and print out the previous name and the number. Okay, so when you move to a new name, we reset the count to not 0, but to, come on, don't be shy. You move to a new name, why is 1? Thank you. Don't reset it to 0, because when you move to a new name, that person is 1. That's the first instance of the new name. So reset your counter in this case to 1. Okay? And what happens when you move to a name, but it's the same as the previous name? What do? Over there. Yeah, you. What do? Very good. You add 1 to count. Okay, so that's what we'll do. So after we have finished inserting all the names, we will iterate through the names. And there's always this nasty thing of initialization. Okay, so you have to worry about the case where you're at the beginning of the list. So in this case, he says, if we are not at the beginning of the list, then, as this gentleman said, if our current name is equal to our previous name, PN stands for previous name. And in your code, please do not abbreviate like this. Sorry. And you can't even kill it. Usually it's on Do Not Disturb. It is now. So please don't do things like PN. Please write it out. So PN stands for previous name. So if the current name is equal to the previous name, we increment count. Otherwise, we have come to a new name, so we print out the old name and the count. So we print out the old name and the count. Then we initialize previous name to the new current name and reset count to 1. Okay, so that's the case where we are not at the beginning of those, not at first element. If we are at the first element, it's this case right here, first element. And in that case, we simply set the previous name equal to the first element in the set, and we set count equal 1. Okay? So that is what is going on there. Now, notice at the very end, there is a final if statement after the for loop. Some of you had this issue on other labs, or I believe on the tests. So the problem is when we drop out of the loop, what happens with the last person? That last person has not yet been printed out when we reach the sentinel value. So what he's doing with this last statement is if there's at least one person in the set, if the set was empty, we don't want to print out anything. But if the set wasn't empty, then we have not yet printed out the last person in the set. So that's what that if statement is all about, is we need to pick up the last person in the set. So this statement right here prints the last person in the set. Now, this code was much more complicated than the previous code using a map. Generally, you would not use a multiset, but it was a nice example of using a multiset, so you could at least see a multiset in action. But this is definitely not the preferred way to implement code that counts the number of players who's with a similar last name. This code is definitely more succinct. Okay, so I am not going to go through the example maps and sets together because you will get to do that as part of the after class activity. So we're going to skip to this very important point, which some of you will ignore in your lab to your chagrin. So you should pick up your head at this point and definitely pay attention, because this will get you into trouble. Generally, you will need to use pointers to the val part. I will modify his headline. You should use pointers as the val part of a map if the val part is an object. If it's a primitive type like an integer, there is really no need to do that. In fact, there's really not a need to do it if it's a string. But if the val part is an object, often you will want it to be a pointer to that object. And in fact, I do have to go back and quickly talk about what his maps and sets were together. So what his example of maps and sets were together was, instead of printing out the last names of the players and their counts, he actually wants to print out the names. He wants to print out the roster of players in alphabetical order by last name. And then he also wants to print out the first names, and those first names should be in alphabetical order. So you see here for Abdullah, there's Hamza and Hussein. Hamza comes first. Similarly with our atoms. There's a number of atoms. We print out all the first names in alphabetical order. So the way he's going to do this is he's going to have a map that keeps track of last names, whose key is last names. And what do you think? How do you think he can keep track of the first names and sorted out? How can he keep track of sorted names, first names? The value field needs to somehow be the names. Is all first names. With that last name. But we want to keep those first names in sorted order. How do we do that? A set. So the value field is a set of all first names with that last name. That will keep the first names in sorted order. Okay, so here it is. The last names is the key, and here is a pointer to the first name set. You can see he's using a type def up there to say that first name set is a set of strings. So this is keeping a set of first names. And we're using a pointer to that set. Okay. So, whoops, that's certainly not what I wanted. Okay. So, it's pretty simple. He reads the first name and last name again. He finds the last name. If the last name does not exist, he creates a completely new first name set for that last name, and he inserts the pair into the map. Now, he does not yet, this code does not insert the first name into the set. We haven't done that yet. So it simply adds, this is empty. Okay? Currently empty. So when he inserts the set into the map, that set is empty. Okay? But he has set first names to point to that set. If the name is already in the set, then, if the name is already in the map, then he sets F names to point to the pre-existing. So this one sets first name to point to the pre-existing first name set. For that last name. Okay, so when he comes out of this if statement, which is right here, he knows that first name points to the correct set. And then he inserts first name into that set. So, while the code you may have to look at this code a little more closely after class, conceptually it's really not that difficult. Look up the name, the last name, and then insert the first name into the first name set for that last name. Okay, and I'm not going to go over the code for printing out. I think you should be able to do that on your own. So now we get down here and he's making a point that he used a pointer for his value field rather than an object. And he is going to show you why, all the ways you can go wrong if you don't use a pointer. Okay, which, as I say, will affect you too if you don't use a pointer. So he says, let's go ahead and not use a pointer to first name set. We're simply going to store a first name set as the value field. And the code is pretty much the same, except, actually it is, I think, exactly the same, except that up here, he was using an arrow because he had a pointer, and down here he's using a dot because he has an object. Otherwise, the code is identical. Okay? But when he prints it out, things go wrong. So here's a very simple example. He has his input consists of two names. Okay? So you would expect when it prints out, it should print out like this because that's in sorted order. But in fact, when he runs his code that doesn't use a pointer, he comes out with Andy Allman, the Adam that was associated with Anderson, and the last name Allman, which is totally wrong. Okay? Not only is there not enough names, but he's taken two people and, in effect, taken half of each of their identities. Okay, so what's going on? Okay, well, there's a number of things going on here. So he starts with the most egregious thing, which is that you always are, with your first name set, you are always inserting that same set. Okay, so if we kind of trace through the code, we first read Adam. The first person we read is Adam Anderson. And when we insert into last names, first name is currently empty. Now, what it does is it makes a copy of F names. When it's an object, it makes a copy of F names. So right now, it put an empty set in there. Now it says fnames.insert first name. So fnames gets Adam. But the last name Anderson had a copy. It did not have first names, it just has an empty copy. When you insert Adam into first names, nothing happens to Adam's copy. It stays empty. They're two totally separate entities. Because Anderson has a copy of F names. So when we modify F names down here, we're not modifying Anderson's copy of F names. We are modifying this original F name set. So what do you think is going to eventually happen to this F name set? What's it going to have at the end of the program? No, it's not. Let's do the second one. So let's do some more iteration. So the next person is Andy Allman. So next we read Andy Allman. Okay, so we do a find. There's no Allman. We insert a make pair. And what does first names now consist of? Well, we make a copy of first names, and Allman gets a copy, and that copy contains, whoops, Adam. Because that's what first name currently has, is Adams in it. So now we again insert the first name, which is Andy, into first names. Well, Allman doesn't know about that. Allman has a copy. Not only does Allman have a copy, Allman has a copy that is not a correct thing. You wanted to give Allman an empty first name set, but instead you handed Allman a copy that had what is in first names. Can you now infer what is going to be in first names at the end of the program? What are we accumulating in first names? All the first names in the file. That's not what we want to be associating with the last name. Okay, so the reason we got at the end, we got Adam Allman, is because we had Allman and Allman got Andy. I'm sorry, Allman got Adam, the wrong first name. Okay? So the first issue is that we can't just go assigning F names to it. So there's a very simple fix for that. You can simply assign the constructor. An fn set is a set of strings. So what we're doing here is we're assigning a copy of the empty set. So at least we're going to fix the problem of not always assigning first name set, which contains all of the existing first names, to last names. At least we'll be attaching a copy of the empty set. But that's not going to be good enough. Okay, when we say F names equals last name second, what we get in first names now is a copy of the set associated with last name. Because it's not a pointer, it makes a copy of that set. So what we end up modifying is the copy. So right here when we say fnames.insert, we modify the copy. We don't modify the actual set associated with last names. So when we print it out, we get nothing. And why is that? Because every last name still has an empty set. We never modified any of the sets associated with last name. Okay, because this code right here, right there, that code got a copy of the set associated with last name, and therefore it never modified the set associated with last name. So every last name ended up with an empty set. So when we went through the code, nothing ever got printed out because no last name had a first name associated with it. So when we printed out our output, it was empty. Okay? So you could fix it by instead writing lnit second dot insert, and that turns out that it returns the object associated with the last name at it inserts. Or you could use something called a reference variable, which we're not really going to discuss in this class, but you can have reference variables. They have an ampersand in front of them. And they're pretty confusing, so we're not going to go over them. You can read about it. But the bottom line is that it is devilishly difficult to write correct code that involves using a non-pointer. Okay, and there's yet a third problem that you would have when you went to print stuff out if you were not using a pointer. So if you are not using a pointer, then it turns out the code works, but this statement right here is always getting a copy of the set. And making all of those copies for a big roster is expensive. So this fragment makes a copy. This code makes a copy of the entire set. Ugh. Okay, because that's a total waste of time to make a copy. So again, you would have to do some fancy coding to avoid making the copy. And it just gets to be very difficult to write both correct and efficient code that does not involve using a pointer. So the bottom line is you've got to get used to using a pointer. So going back to here, use pointers as the val part of a map if the val part is an object. Now again, that's not necessary for a string, but pretty much for everything else it is. But for pretty much everything else it is. Okay, so you're going to have to get used again to using pointers. I know I went through that somewhat quickly. You should take a look at it again. But the bottom line is that when the val part is an object, then every time you retrieve the val part, you get a copy of the val part. And when you modify the val part, you end up modifying the copy, not the original val object. So the big problem with not using a pointer, the big problem with val being an object rather than a pointer to an object is that you always get a copy of val rather than the original object. Okay? Hence, modifications will be to the copy rather than the original object. And you will lose the changes. So, bottom line, use pointers to your val objects. Questions about that? Okay. And just quickly, when you insert into a set or into a map, you sometimes want to know whether the key already existed or not. And the insert actually returns a pair. The iterator is a pointer to the inserted key. And the bool is whether the insert succeeded. Okay, so the bool indicates whether the item was inserted or not. If the key was already there, the insert failed, and the iterator will be to the key that's already in the set. So it's a pointer to the inserted key, or if the key pre-existed, then to the pre-existing key. So you actually get back a pair from your insert that allows you to determine whether that key was pre-existing or not. So sometimes, rather than doing a find followed by an insert, you might just try to do the insert. Why might you just try to do the insert rather than a find followed by an insert? So on one hand you have insert, the other hand you have find followed by an insert. Which do you think is more efficient? Well, is one instruction more efficient or is two instructions more efficient? One. So this is more efficient. And there's no price to be paid because if the object was already there, nothing happens. You simply check the bool value and you'll find out whether it was already there or not. So oftentimes you'll simply insert into the set and then just check the return value to see whether it was already there or not. Now, when you do this in a lab, I don't care whether you do find followed by insert or whether you just do insert. But again, we talk about efficiency a lot in this course, so I will tell you that that's a cute trick, is that you can just do an insert always and then check the return value to see whether it succeeded or failed. Okay, so the last thing is that you have another way to insert into maps rather than using that hideous make pair. Okay, and the way you can do it is you can use array notation. So they are called associative arrays because they look just like arrays. So an associative array is really just a map that is treated like an array for syntactic purposes. Okay, and the index is now the key. So the index, what used to be a number, is the key. And then, of course, the other side, this is the value. So that's another way that you can assign to maps that's a lot easier than using insert. Okay? Now, I love this notation. It is a lot easier to use than insert. But there are two pitfalls that you need to be aware of. Okay? So, here are the two pitfalls. Two pitfalls of using a map as an associative array. Okay, first one, if the key is pre-exists, then its value is replaced. Okay, there is no error message or no error return value, which you might get that you would get with insert. So if you tried it with insert, it would fail because the key already exists. But if you do it with a map, it assumes you just want to replace the value. So you need to be careful about that. If it really is an error because you're trying to insert a second key, then you really need to use insert because, as I say, this will happily replace whatever the previous value was for that key with a new value. And Dr. Planck illustrates that with golfers. So he is computing golfer scores, and what happens is that two golfers, Tiger Woods and I think it's Vijay Singh, end up ultimately with the same score. I can't find it. At any rate, the problem is, in his golfer example, Tiger Woods and another golfer end up with the same score, and so he's indexing on score, and when he assigns Tiger Woods to that slot, he loses the other golfer. Or I think it's vice versa. I think actually Tiger Woods came first, and the other golfer came second, and when he assigned, he overwrote Tiger Woods, which was no good. So you have to be careful about that. The second thing you have to be careful about is that when you retrieve a value, so if you retrieve a key, if you retrieve the value of a non-existing, the value of a key that does not exist, okay, C++ inserts the key into the map assigns it a default value and returns the default value. Okay, that's not really good because you may not be able to determine if that default value is a real value or not. Let's say I want to know how many tournaments Jack Nicklaus won last year. So I say if golfers, and let's say that the value is the number of fields, okay, let's say I say C out. I'm almost done. I say C out, golfers Jack Nicklaus, and let's say Jack Nicklaus wasn't in the map before. Well, he's now in the map with an entry of 0. And you print 0. But really, you probably wanted to say Jack Nicklaus is retired. He's not on the tour. not Jack Nicklaus won 0 tournaments last year, because that implies that Jack Nicklaus was an active golfer. So the problem is you got a value back for Jack Nicklaus, but you had no idea whether that value indicated that he was in the map and had won 0 tournaments, or whether he was not in the map and he just got added to the map. So those are the 2 pitfalls you need to be careful about. If you need to know, you would do a find in this case rather than use the associative thing. So in this case, instead of using the associative thing, you would say if golfers dot find Jack Nicklaus rather than using the array notation. But as long as you don't have one of those 2 cases, it's fine to use the associative array notation. Now, have a nice spring break. There is going to be a problem from a midterm. It's a short one that hopefully won't take you very long on Code Assessor. I'm going to make it due Saturday at 6 a.m., effectively Friday night. So you'll have 2 days to do it. It's not a long problem. It will give you some experience using sets and maps. It's already up, but I will have to post the name of it to the course website, and that will be there in a few minutes. I also will do the regrades of the quiz this afternoon.